Hi all! In this video we will go over how to determine the electric field due to a conducting sphere of radius r placed on a charge of minus q. So the problem is a charge of minus q is placed on a conducting sphere of radius r, and we want to determine the E field inside and outside of the sphere. So the first thing we need to do is draw the situation. So we're going to have a sphere, radius r, and it's going to be a sphere, and there's going to be total charge of minus q placed on this. So we're going to have more or less a negative jelly of charge spread evenly over the surface of this. So as you remember, with a conductor, electric charge uniformly distributes on the surface. So we're going to have minus q all over the surface of this. So we've drawn the sphere, we've drawn the charge. Now the next thing to do is to draw the electric field. So you'll remember that for negative charges, electric field lines come in and they end on negative charges. So we're going to have the E field coming in like this. It's supposed to be perpendicular to the surface of the sphere at all points, and it's like this, and it's uniform in both angular directions. So we have the electric field, so this is going to be E, and we can now pick a Gaussian surface. So let's start with, for r less than the radius of the sphere, we're going to solve for the E field. Now inside the sphere there will be no charge, so if there is no charge enclosed, then we won't have any electric flux. So we'll write down Gauss's law. E dot dA equals Q enclosed over epsilon naught. So inside we won't have any charge enclosed, so this right hand side will just be equal to 0. We will choose a Gaussian surface inside of this, so it's a smaller sphere that's in here. So that will have some surface area which will be equal to 4 pi r squared, and then it's going to be multiplied by the E field. So at any non-zero point of r, so this is for any radius from 0 to big R, the flux has to be equal to 0, and the only case that this can happen, since the radius will go from 0 to big R, is for the E field to be equal to 0. So inside of here, the E field 0, and this is something that you know from conductors. The electric field inside a conductor is equal to 0. So now we can do the second part, where we now draw a Gaussian surface outside. So it'll be a concentric sphere that encapsulates this conducting sphere. So now we will solve for the E field for r greater than big R. So we'll come over here, we'll rewrite Gauss's law. So it's E dot dA. That's going to be equal to the charge enclosed over epsilon naught. So on the right side, the charge that we enclose is equal to minus q over epsilon naught. And then over here, we chose a Gaussian surface such that the electric field is the same value at any point on the surface. So we can pull that out of the integral. And then we just need to do the surface area, which is just going to be 4 pi r squared. And then we can solve for the magnitude, which is going to be minus q over 4